Hello and welcome to this Urbano software webinar. Today's topic is the hydraulic calculation with the new SWMM module integration. So today, of course, after this short introduction, we will be going to the live presentation. And afterwards, in the end, we will have questions and answers. So if you have any questions about the software, please use the questions tab to write your questions, and we will do our best to answer all the questions after the live presentation. So Urbano software has been in development for more than 30 years. And its unique advantage is that you have a design of plan and profile together with the hydraulic calculation, which allows you to calculate and optimize the pipe network. Also, in the same package, there are many analysis tools, so you can analyze that data with graphs, labels, data tables, and many additional ways. Also, there are lots of possibility to import and export pipe network data and also other data with GIS systems, CAD, hydraulic modeling software, and also BIM software. And you can customize almost anything or anything important. So profiles, labels, data tables, styles, catalogs, pipe and manhole catalogs, and many other things. In the user interface and in the software itself, you can customize by yourself. Okay, now we are getting ready to start with the live presentation. So my colleague Rino Nemernik will take the lead.
Thank you, Michael, for your introduction. Hi and hello to everyone. My name is Rino and welcome to another Studio Ars Urbano webinar. As you probably already know, Urbano is a software for detailed design, analysis and hydraulic calculation of storm and sanitary water and gas distribution networks. And today's topic will be integrated SWMM 5.1 hydraulic calculation in Urbano Canalis. In the following 50 minutes of live presentation, I will show you 5 different examples of storm and sanitary networks, including gravity pipes, pressure pipelines, and open channels. This will be a more advanced webinar, so if you're interested in getting to know the Urbano software and how to start, you can watch our previous webinars on our Go to Stage channel. So let's start with the live presentation. Here in this drawing, I have one Urbano pipe network created with an older version of the software. So basically one old project made before we had this integrated SWMM calculation. In this first example, I would like to focus on the basics. So how to start and how to resolve the errors that may occur to you while working with this new functionality. Okay, so let's take a look at this drawing. I will zoom to plan. And here we can see that this system is completely defined. We have the pipes set, we have the manhole set. Also, all the elevations are set for the terrain and for the invert elevations. And also using these really nice labels, we can see that also Urbano catchment areas are defined. If we take a look at the profiles, we can see that all the data is here. So we can see it in the profile data tables and also all the graphical elements. We can see the pipes, the manholes, and also terrain elevations. Okay, let's now analyze this system a little bit. And to analyze any Urbano pipe network, it is always the best to use the data tables. And here you can have many different data configurations. So when you open the data tables, you can choose between these predefined data tables. So let's take a look at section geometry, where we can see all the data about the sections like invert elevations, slopes, diameters, and so on. But also you can switch to a different data configuration. For example, the one for the pipes, where we can see all the data about the pipes like inner, outer, and nominal diameters. Also, let's switch to a different data table with the data for the catchment areas. And here we can see that we have 3 catchment areas defined that are also house influence area, which means that besides the runoff coefficient, here we also have defined the population density in number of people per hectare of the area. Also, here we have one industry influence area, where we don't have the runoff coefficient or the population density, so just the area of this catchment. Okay, so let's now close the data tables and let's move to Canalys. So Canalys is a panel where you have all these functionalities related to hydraulic calculation for storm and sanitary networks. So the first function that I will show you is flow calculation. So here you can set or calculate flows both for storm and sanitary networks. For the rain flow, I decided to use this simple rational method, and we call it simple because in this method, rainfall intensity is a constant value. So this is basically CIA method, and when you multiply these three numbers, you get the rain flow calculated for each section. For the sanitary flows, I decided to use this waste flow influence areas methods. And for the house wastewater flow, we defined this wastewater flow coefficient in liters per second per 1,000 inhabitants. We also have the house influence areas defined and distributed to each section. We have the population density that we defined in the catchments. And again, we have calculated this house wastewater flow for each section. And for the industrial wastewater flow, we also define wastewater flow coefficient in liters per second per hectare. And for this one section where we have the industrial influence area defined, we have calculated the industrial waste flow. So when you set or calculate the flows, you can group them in so-called flow scenarios. So here I created three such scenarios. The first one I called storm, where I have only this simple method included. Then the second scenario, where I have excluded the simple method because this is for sanitary flows. And then the third scenario is called mixed, where I have everything included. Okay, so let's close now this dialog and let's go to hydraulic calculation. So it's important to say that this function that I will now start is not related to SWMM in any way. So this is standard Urbano Canalys, steady state hydraulic calculation according to Darcy, Weisbach, and Colebrook-White equations. So here in this dialog, you can select what is the flow scenario. So you can go with sum of all defined flows, or you can select one of these predefined flow scenarios. I will go with sum of all defined flows, which is basically the same as mixed scenario. For the hydraulic calculation type, you can choose between pipe sizing or according to existing diameters. And let's say that we have this network already built. So let's go with according to existing diameters. Let's select everything and let's click calculate. Okay. And now we see that the software is giving us some warnings and some errors. So we have a warning that in this section, total flow is equal to 0. And also we have some errors that the flow is greater than maximum for defined pipe. Still, we can save these results. And if we close this dialog and open our standard Urbano data tables, if I switch to section hydraulics and expand this node column and sort the data table by this data, we can see these same errors and warnings. So let's take a look at this warning and let's zoom to plan. So here in this section, it says that the total flow equals to 0, but this is okay, this is just a warning because later on we will have an outfall section here. But here we have some errors, so let's take a look at those. Let's go to profile of these sections, and we can see that for these sections, this standard Urbano hydraulic calculation couldn't compute the hydraulic values for these sections because they are surcharged, so they are 100% full. So you can see that for all other sections, the software calculated velocities, filling heights, and filling percentages, but for these ones, we don't have any hydraulic calculation values computed, as it can be seen in the missing of the hatch in these pipes. So this standard Urbano Canalys calculation cannot compute the surcharged pipes, And also what you can see, it cannot compute water levels in the manholes. So let's now go to SWMM hydraulic calculation that is integrated in Urbano. So first of all, let's go to this standard canalis hydraulic calculation and let's reset these results. Okay, let's close this and let's go to this group of commands related to SWMM. So hydraulic calculation according to SWMM. And here again, you see very similar dialog. So you can choose direct inflow or dry weather scenario. So you can use the flows calculated with standard canalis for SWMM calculation. So for example, I will select for direct inflow sum of all defined flows, or I can do it like this and say that dry weather scenario is sum of all defined flows. So it's up to you where you want to write these flows, basically in what field in SWMM EMP file. But be sure not to do it like this. So if you do it like this, in this case, you will basically double your flows. So this is something you don't want to do. But for example, if you would like to split your flows, for example, for direct inflow, we can select the storm scenario, and for dry weather, we can select the sanitary scenario. So this is what you can do, for example, if you want to define different time patterns or different time series for each scenario. I will keep it simple and I will say that sum of all defined flows is direct inflow. So before we click calculate, let's check the options button. And here you can see all the SWMM available options. But for now, let's just check this one out. So routing model. So for the routing model, you can choose between steady flow, kinematic wave, and dynamic wave. And kinematic wave is default, so we will go with this one. Okay, so let's now click calculate and notice that the software will give us a lot of errors here because it says that for each subcatchment we have undefined object. So let's take a look why this is happening. Let's close this and let's go to subcatchments dialog, and here you can see all the catchment areas defined in Urbano with all the parameters available in SWMM. So if I select all these three catchment areas, we see that we have no rain gauge defined. But for this calculation, where we use the rain flows already calculated with canalis, we don't have to have rain gauge. So later I will show you how you can use rain gauge, but for this example, we'll just close this. Let's go to hydraulic calculation according to SWMM. Let's go to options. And here, I will turn off this option for SWMM to calculate rainfall and runoff. So just turn it off because we are using the rain flows and sanitary flows already calculated with standard canalis. So let's click OK and let's now recalculate. Now we can see that we have some other errors here. So for each section, the software is saying that we have invalid roughness. And this is something that will happen only, let's say, to existing users that are using the, let's say, like I said in the beginning, an older project, or for example, if they are using the pipes and the pipe catalog from an older version of Urbano. If you start a new project in new version of Urbano, this will not happen to you. But let's show how you can resolve this. So if we go to workspace and open the data table for roughness data, here you can see that we have only Darcy-Weisbach roughness coefficient defined, and we have no Manning and no Hazen-Williams. So we have to go to pipe catalog and refresh the catalog to the newest version. So these are the pipes that are used in this project. So if I pick on this one, we can see that we have just one pipe roughness data, and this is the data related to Darcy-Weisbach. So if we want to update the catalog, just pick on the top branch in the pipe catalog, right mouse button and click refresh. So now if I pick on the same pipe, here we can see that we have two additional data regarding the roughness. So Manning roughness coefficient and Hazen-Williams roughness coefficient. And of course, for the SWMM calculation of gravity pipes, we need this Manning roughness coefficient. So these are the pipes that are, let's say, old pipes. But of course, if you create a new pipe or if you start a new project in new version of Urbano, this data about all three roughnesses will be here by default. So this error will not happen to you. But if you're using your own pipes that you copied from an older version of Urbano, be sure to refresh your disk catalog as well. So let's save these changes now in the catalog, and let's go back to Canales, and let's go back to hydraulic calculation according to SWMM. Let's now again rerun the calculation, and now we have one more error still. It says that this node here has more than one outlet link. So let's check this one. Let's go to this node here, and we can see that this node has these two outlet sections. So for the dynamic wave, this is okay, but for the steady flow and kinematic wave that we are using here, we cannot calculate this without setting the divider. So let's go to function for hydraulic equipment. So this is a function where you can set all the SWMM available equipment, both for nodes and for sections. So for example, if I select this section here, I can set it up to be a plain section or conduit with all these SWMM available parameters, or I can set it up to be a pump, orifice, weir, or outlet. Also, if I select a node, for example, this one here, I can set it up to be a plain node or junction with all of its SWMM available parameters, or I can set it to be outfall, divider, or storage unit. Let's set divider, and let's define a type of this divider. I will use a cutoff, but you can also use tabular, weir, or overflow. For the cutoff type, we also have to define a cutoff flow. So let's set this for 60 liters per second. So this means that in this section, in the main section, we will have 60 liters per second, and the remaining flow will go to the diverted link. So we have to set what is the diverted link. And from this drop-down list, I will select this overflow section. So when I click apply and close this dialog, we can see that the custom block automatically appeared here, representing the divider. Okay, so let's now again go to hydraulic calculation according to SWMM. And now when I click calculate, we will finally get some results. So let's save them and let's analyze them in plan and also in the data tables. So if I zoom to plan now, because of this divider here, we can see that here we have exactly 60 liters per second. And here in the overflow section, we have the remaining flow. Okay, let's also check the results in the data tables. But now I will switch from this section hydraulics data table to this SWMM section results. Now we can see that we have all the flows calculated, water depths, velocities, volumes, and also capacities in the pipes. So we can see that some pipes are also 100% full according to this calculation. But if we zoom to profile, now we can see that this calculation, this SWMM calculation can of course calculate the pipes that are surcharged or 100% full. Also, if we switch to the results for the nodes, here we can see that the software calculated water depths and head elevations for the manholes and also flooding data. So we can see that in these manholes here, we have the water coming out from the manholes. But if we take a look at the profiles, we can still not see the water levels in the manhole. And again, this is happening only because I'm using an older drawing created with an older version of Urbano. And if you start a new project in new version, this will not happen to you. But if you have older configurations of the profiles, be sure to open at least once each configuration. And when you edit it, you will see that the software will say in the command line that new components and new parameters have been automatically inserted, like open channels, grids, piezometric lines, water levels in the manholes, and so on. So it's enough to just open each configuration once, click OK, and save those configurations. For example, if you are using the disk repository, then be sure to update this disk repository as well. So let's now just check. I will select this manhole, this one here. Okay, and we can see that this filling level for the manholes is now here, and by default it is turned on. So let's just click apply, and you will see that the water levels in the manholes will appear. Also, I would like to pick on a pipe here, and I would like to change this hatch type from ANSI to solid. to see these water levels a little bit better. Okay, and because we use the kinematic wave equation, you can see that the water levels in the pipes are constant between the two manholes, so the water level cannot change in between the two manholes. But let's now check the dynamic wave. So let's go to hydraulic calculation according to SWMM, and in the options dialog, we will switch from kinematic wave to dynamic wave. Notice when you switch to dynamic wave that additional options regarding the dynamic wave will become available. I will leave everything as default and just click calculate. Now, again, we have one error regarding the dynamic wave calculation. It says the drainage system has no acceptable outlet nodes. So, to be able to run hydraulic calculation according to dynamic wave, we have to set the outfalls. So let's select this two last node of the system, and from the drop-down list I will select outfalls, and I will set the type to free, but also it can be normal, fixed, tidal, or time series. Let's click apply, and let's close now this dialog. And if we take a look at plan, we can see that the custom block for the outfalls automatically appeared. Let's check this node in the profile. So this is the last node of the first array, this one here. And we can see that for this node in Urbano, we have a manhole defined. But in EPA-SWMM, the outfall nodes cannot have manholes. So it is recommended to delete the manhole from the outfall node. So I will just select this manhole and delete it like this. And also I will redraw the profile so that this graphics update. Okay, so now we have everything ready to go to hydraulic calculation according to SWMM. Let's click calculate and let's save the results. Now you can see that we have a lot of results that are different, of course, because we are using the dynamic wave, which is theoretically most correct method. So let's close this and let's check the results in plan now. So now you can see that here we don't have the 60 liters per second anymore, because in the dynamic wave equation, the divider is ignored because everything is computed by the equation. Okay, let's take a look at the results at the data tables now. So if we take a look at SWMM results for the sections, again, we can see that we have some pipes that are 100% full, but now because of the dynamic wave, these water levels in pipes and manholes look different. Now the water levels in the manholes doesn't have to be constant. Now we have these piezometric lines that define the water levels in the pipes and in the manholes. Okay, and let's now switch also to results for the nodes. And if I sort this data table by flooding data, we can see that according to the dynamic wave equation, we have no flooding of this system. Okay, so this would be it regarding this example. And now I would like to switch to a different example where I would like to show you how we can use rain gauges and time series to let the EPA-SWMM calculate the flows. So again, here we have one really nice Urbano project. If we take a look in plan, we can see that everything is completely defined. We have the pipes, we have the manholes, we have the invert elevation set, and also we have all the catchment areas defined. If we take a look at the profiles, again, you can see that everything is set here. We can check all the data, and also we can check everything in the graphical part of the profile. So first of all, let's switch to Canalis panel. Let's switch to this group of commands regarding EPA-SWMM hydraulic calculation. So first, let's open the catalog of curves, time series, and time patterns. And like the name says, here is the dialog where you can create all the EPA-SWMM available curves, time patterns, and time series. And here you can see that I have one time series already created. So this is basically one IDF curve for the return period of 5 years for this area. And you can see that we have the recorded value each 5 minutes. And we see that the peak value is 165 millimeters per hour. So it is important to say that when you are defining this rainfall intensity time series in this dialog. So for the use in EPA-SWM, be sure to define it in millimeters per hour. In some other functions in standard Urbano Canalis, we usually define rainfall intensities in liters per second per hectare. But in this function, you have to define it in millimeters per hour. So let's click OK. Let's click OK. And let's now define a rain gauge. So to define a rain gauge, it's very easy. Just click Add. You can define the coordinates of it if you want, but it's not essential. For the rain format, you can choose between intensity, volume, or cumulative volume. I will go with intensity. For the time interval, I will set the interval to 5 minutes because that's how we have the time series created that I just showed you. So let's save this rain gauge and let's now open the subcatchments dialog. So like I already said in the previous example, this is a dialog where you can see all the catchment areas defined in Urbano and all the EPA-SWM available parameters. So you can define precisely all these parameters for each catchment or subcatchment, or you can select more of them or all of them and set the same values to all the catchment areas. So I will set the same rain gauge, the one that we just created, to all the catchment areas in the selection. Here you can also define infiltration data. So you can choose between these 5 methods, including Horton, green amped, and curve number. Let's go with curve number, okay? And let's save these changes in the subcatchments. The only thing that we have to do left is set the outfall in the last node of the system because we are going to do a dynamic wave calculation. So let's open hydraulic equipment. I will select this node here, and from the drop-down list, I will select outfall with the type free. So let's click apply, and now we have everything ready to go to hydraulic calculation according to SWM. I will zoom to this profile so we can immediately see the results here, and let's open the hydraulic calculation according to SWM. This time, we will leave this direct inflow and dry weather scenarios empty because this time we will use this option for EPA-SWM to calculate rainfall and runoff based on the rain gauge and the time series that we defined. For the infiltration model, we will use curve number. For the routing model, we will use dynamic wave, and we will do a 2 hours time simulation with reporting step set to 5 minutes and runoff step for the wet weather set to 1 minute. So let's click OK, let's click calculate, and let's save these results. So now you can see that we have 24 sets of results for the nodes, for the sections, and for the catchment area. So let's take a look at the data table. So this is a standard data table where you have all the data for all the elements in the selection for just one time of the simulation. And with these arrows left and right, and with this drop-down list, you can move through time like this and preview the results for the selected time. When you want to save the values, the results for that time period, just click apply, and then those values will be seen in your standard data tables, in the profiles, in the labels, and so on. Also, we can switch to a default preview for the nodes and check all the results for the nodes like water depths, head elevations, and flooding. But this time also we can switch to a default preview for the catchment areas, and now we can see that the EPA-SWM also calculated precipitation, infiltration, and runoff from the catchment areas. Let's go back to default preview for the sections, and let's switch to the second type of the preview, which is preview by object. So here you can select one object. It can be any node, section, or catchment area. And I will select this last section of the system like this. And now, for example, we can sort it by data. And again, we can see all the data, but now just for one selected element for all the times of the simulation. And here we can sort it by, let's say, flow, and we can get what is the peak flow for the selected section. And for this last section, that is 10 minutes into the simulation. So now maybe we can go back to the standard preview, and from this drop-down list, we can select the 10 minutes. And when we click apply, those values will be applied in the drawing. So let's check our profile. And now we can see the results that are saved for the peak flow of the last section. Okay, let's now close this preview like this, and let's switch to the third type of the preview, which is preview by variable. So you can select any data for sections, nodes, or catchment areas. I will go for section flow. Now I can select multiple elements, in this case multiple sections. So let's select this one, this one, this one, and the last one, like this. And now in the same data table, we can see all the selected elements for just one selected data for all of the times of the simulation. And in this really nice data table, you can check everything, compare it, analyze it, and if needed, like any other data table, you can select everything and, for example, copy to Excel or any other Microsoft application. Okay, but every time when we do this time simulation, it is nice to have some graphs. So let's switch to time series graphs. And here you can see that you can select up to 3 data for sections, nodes, and catchment areas. So let's say for data number 1, I will select section flow. For data number 2, I will select node depth or water level in the manhole. And for data number 3, let's select catchment area precipitation. So now you can select for each data, you can select one or more elements. So let's select this last section. Let's select this last node or the outfall. And also let's select one catchment area, this one here. And now in the same graph, you can see all these different values shown in different graphs. You can analyze it. And of course, if needed, you can draw these graphs to CAD. For example, all the values on the same graph or each value on a separate graph. So let's take a look at it. And if needed, of course, you can plot these graphs and put them in your project. Okay, so let's again switch to the following example where I will show you very similar thing, but now on a much bigger project. So this is a real project made by Urbano customers here from Croatia, the designing company Hidroeko from Zagreb, Croatia. And if we take a look again in the plan, we can see that everything is completely defined geometrically. You can see all the pipes, all the manholes, and all the elevations. And again, in these labels, we can see all the defined catchment areas. Okay, let's now draw profiles for this network. So to draw profiles in Urbano, it's extremely easy. You have to just select the profile configuration and everything is stored inside, from the data to the scale to the colors, so everything. And I will select the entire system and I will draw all the profiles according to array topology. So let's just click draw. Let's define the insertion point, and these 67 profiles will be drawn in a matter of seconds. Okay, so let's close this and let's take a look at these profiles. So again, we can see that we have everything defined in the profile data table. And also if we take a look at the graphical part, we can see all these pipes, all these pipe elevations and the manholes that are set. Okay, let's see what else we have in this drawing. Let's switch to Canalis panel. Let's go to function for catalog of curves, time series, and time patterns. Here you can see that we have one time series already set in this drawing. So let's take a look. And now you can see that we have the recorded time of 40 minutes with the constant rainfall intensity of 50.4 millimeters per hour, which equals 140 liters per second per hectare. So let's click OK to close this dialog, and let's check the rain gauge. So we have one rain gauge defined with these coordinates, and we have this time series set for this rain gauge. Also, if you go to subcatchment dialog, here we can see that for all these subcatchments, we have this rain gauge set, and this time for the infiltration data, we will use Horton method. Also, if you go to network elements data, a function where you can see all the equipment that is set in your network, we can see that besides the nodes and the sections, we also have one outfall defined in the last node of this system, and the type is set to normal. So we have everything to go to SWMM hydraulic calculation. And again, we will not use any flows calculated with standard canales. Let's check the options. We will use the option for SWMM to calculate rainfall and runoff. Infiltration model will be Horton. Routing model will be dynamic wave. And again, we will do a 2 hours time simulation with reporting step of 1 minute and runoff step for wet weather of 1 minute. So let's click calculate. And after a few seconds, we will also save these results. So now you can see that we have much more results than before, 120 sets of results for nodes, sections, and catchment areas, because we did the calculation each minute. So now that everything is saved, let's first switch to preview by object. Because we have so many results, I like to do it like this, and I like to select some section. Usually, I like to select the last section of the system, this one here. And then for it, I like to sort this data table by flows, so I can get what is the peak flow for that section. And for this section, this is 46 minutes into the simulation. So let's go back to standard preview. And from the drop-down list, let's select 46 minutes. Let's apply the time. And now we can see that those values will be saved in the drawing. So you can see them in your standard data tables, labels, and of course the profiles. So let's zoom to this biggest profile here. And now we can see all these water levels appearing for the pipes and for the manholes. And if we take a look at the last section for which we applied the results for the peak flow time, we can see that this last pipe and this complete array, this complete profile is not surcharged. But let's keep analyzing. Let's select the whole system and let's sort by capacity data. And we can see that we have some pipes that are 100% full. So let's zoom to profile of those pipes. And here we can see that these pipes in this profile are surcharged. They are 100% full. And we can see that the water is starting to go up in these manholes, but still there is no flooding. We can check that also in the data table. Let's switch to the default preview for the nodes. And if I sort this data table by flooding, we can see that we have no flooding for this system. Let's now switch to time series graphs, and let's draw one flow graph for the last section. This is always really nice to have. So let's select the last section of the system. And here we can see this flow wave going through the last section of this system. So let's also draw it in CAD and let's place it here. And here it is. We can see the flow wave going through this last section for the 2 hours simulation period. Okay, let's again switch the drawings. So now we are having a sanitary system. Again, this is a real project made by the same designing company that did the last one, so HydroEco company from Zagreb, Croatia. And let's take a look at plan. So now you can see that this is basically mixed sanitary sewage, and we have 2 Urbano plan styles applied. In the red color, we can see the gravity pipes, and in the blue color, we can see the pressure pipelines. So we have in total 3 pressure pipelines, and in the beginning of each pressure pipeline, we have the storage unit defined and the pump station. Okay, let's now draw the profiles for this network. Again, I will just select the profile configuration. I will select the entire network according to arrays, so in total 22 profiles, and I will draw these profiles with this insertion point. It will take a few seconds to draw these profiles. And additional way how you can draw your profiles is by using this really nice selection options from node to node. So using this option, you can basically go from any node to any node in any direction. So I'll go through the last section to the last node of this system, and let's draw the profile here. Okay, let's draw another one. Let's go from this node here through this pressure pipeline all to the last node of this system. Okay, and let's draw this profile here. So now that we have drawn them, let's also check them. And now we can see these 3 pressure pipelines in the profile, and also we can see their storage units in their first nodes. Okay, let's see what else we have in this drawing. So let's switch to Canalys panel, and let's first open the flow calculation dialog. So because this is a sanitary system, we use standard Canalys function to define flows. And we use the point flow. So for each section, we have defined the point flows. And you can see that these flow rates are really small because here we are talking about one village near Zagreb, Croatia. Okay, so let's close this. And let's open catalog of curves, time series, and patterns. And here I would like to show you that we have one time pattern defined. So this is a consumption variation for village. And let's open it. So it is hourly type of SWMM time pattern. We have all these coefficients of variation per hour defined. Okay. Also, we have one storage unit, storage curve or volume curve defined, and we will use this same storage curve for all 3 storage units. Also, we have 3 pump curves defined for each pumping station. And also we can take a look how this look like, and we will be using the SWMM pump type number 3. Okay, so that's it. And let's now go to network elements data to check all the set equipment in this network. So we have one outfall set to free in this last node of the system. Like I said, we have 3 storage units with this volume curve defined for all of them. And we have these 3 pump stations defined with each pump has its own pump curve. And also for each pump, we define startup depth and shut-off depth in relation to water depth in the storage unit. Also, if I select all the nodes in the drawing, and if I pick on time patterns, we can see that for the inflow type direct, we have this baseline pattern consumption defined that I showed you in the catalog of time patterns. Also, if I use the saved selection set to select all the pressure nodes, so all the nodes of the pressure pipelines, we can see that for those nodes, I define the surcharge depth to 200. So it can be any large number because as it says in this description, this parameter can be used to simulate bolted manhole covers or force main connections. And in our case, these are force main connections. So let's close this. And we have everything ready to go to hydraulic calculation according to SWMM. So let's open the function. And this time we will use these point flows calculated in Canalys. So sum of all defined flows as direct inflows. In the options dialog, we can check that we will be using dynamic wave equation. And this time we will do a full day, so 24-hour time simulation with reporting step and run-off step set to 1 minute. So let's click calculate. And now you will see that this time it will take a little bit more time to compute and to save these results because like I said, we are doing a 1 full day simulation. So 24-hour simulation with the run-off step and reporting step of 1 minute. So you can see here that we have 1,440 sets of results. So it takes some time to save this data, but after the data is saved, you will be able to use it like any other data in Urbano. And when we are doing this calculation with the pumps, with the pressure pipelines, it is necessary to put this reporting step and run-off step very small because we want to catch those times when the pump is shutting off or turning back on. But you can see it's saved pretty quickly. And now we can again do some analysis. And like I said, I like to go to preview by object and then select the last section of the system, or basically any section, and sort it by flows so we can get what is the peak flow time for that selected element. So this is 21:30. Let's go back to standard preview. And from the drop-down list, I will select this time of 9:30 p.m. like this. And let's click apply. So we will save these results in the model so we can check them in the profiles or in the data tables, standard data tables, and so on and so on. And here we can see that we have these water levels in the storage unit. We see that the pressure pipelines are 100% full, and we can see these piezometric lines now showing for each pressure pipeline. Okay, let's go back to the dialog, and let's now switch to preview by variable. So for the data flow, I will again use the saved selection sets that I created previously to select all 3 pumps from the drawing. And now in this really nice graph, we can see for all 3 pumps in which periods, in which minutes of the simulation they are active. So this is one really nice information to have. You can see exactly for each pump every minute when this pump is being active, and you can see it in this preview by variable. But also let's draw some graphs. Again, let's draw one flow graph for the last section, this one here, and let's draw it in CAD. This is, like I said, always useful to have. And now I will again use the saved selection sets to select all sections right before the pumps. Okay, and we can take a look how the flow is changing throughout the day in these 4 sections in relation to that consumption time pattern that we defined. So let's draw these graphs separately in CAD, and when they are drawn, we can take a look and see the values in each graph. Okay, so that would be it regarding the pipes. And now I would like to switch to the final drawing today, where I would like to show you that Urbano can also be used for drawing and calculating open channels. So to show you this, let's go to catalog of open channels. And here I would like to show you what are the available cross-sectional types. So you have the standard rectangular cross-section. Then we have the 2 types of trapezoidal. So it can be this standard trapezoidal or this one with the vertical outer walls. We call it trapezoidal box. But for the hydraulic calculation, it's completely the same. But let's say for some other functions, for let's say beam uses, IFC export, NWC Navisworks export, 3D view, clash detection, these outer dimensions are also very important. So very similarly, we have the 2 types of the triangular cross-section and also 2 types of parabolic cross-section. Okay, so let's now show how you can design one open channel. So basically like drawing any other type of the system, but be sure to check this flow type and switch to open channel. All the other options are completely the same, so you can set the elevations directly from selected DTM surface. And I will be using Urbano Terraform, which is our own DTM modeler. But if you run Urbano on top of Civil 3D, you can also use Civil 3D DTM surfaces directly. For the elevations, I will say that the top of the channel is basically 0 below terrain. So basically we will align the top of the open channels with the surface. From the catalog, we can also select the open channel cross-sectional type and size. And now when we click draw, just start drawing and everything will be set. I will do one example that will not make much sense. So basically I will just draw one section of each of these cross-sectional types just to show you how they look like in different views. So we will see them in the profiles and also in the cross sections. So let's draw one triangular, also this triangular box. And for the last 2 sections, let's switch to parabolic and let's draw parabolic and also parabolic box. Okay, so this is it. And now when we have drawn them in plan, we can immediately draw the profile. So let's select the profile configuration. Let's select the active system and let's draw this profile here. We can see that all the channels are aligned with the top of the surface. But if you want to precisely define the invert elevation, you can use standard functions for drawing, editing, or setting the invert directly in the profile. So for example, you can select the entire profile and straighten it, for example, by line or by slope. So let's click apply. And now we can see that I straightened the invert of these open channels, so we have a constant slope. Okay, so let's now draw the cross sections. And to draw cross sections and also to calculate excavation volumes, you don't have to separately set the trenches for these open channels because they are already some type of trench. So let's go to this interactive function, and I will just select few stations in plan like this, and let's draw these cross sections. So let's place them here. And now we can see how they look like in cross sections. So we have this rectangular, 2 types of trapezoidal, 2 types of triangular, and also 2 types of parabolic open channel. Regarding the hydraulic calculation of open channels, you can do it. So let's go to Canalis, but you have to use the SWMM hydraulic calculation. Because if you open the standard Urbano Canalis hydraulic calculation, this message will appear and it says the system elements are missing, because this function is just for the pipes. And if you want to calculate open channels, you have to do it with SWMM calculation. But what you can do, you can use the flow calculation methods of standard Urbano Canalis to define flows. You can use all the available methods, but I will use the simplest one, point flow, and I will just set the 150 liters per second in the starting section of this system. Also, let's go to hydraulic equipment and let's set outfall to this last node of the system, because we are going to use the dynamic wave equation. Of course, you can also define the rain gauges, the subcatchments, basically everything that I previously showed, but let's keep it simple. Let's open hydraulic calculation according to SWMM. We will use this point flow as direct inflow, and let's click calculate, and let's save the results. So now if we take a look at the profile, we can see the water levels in the open channel, and we can see this flow wave happening, because like I said, this example doesn't make any sense because the water is going from this very wide trapezoidal open channel cross-sectional shape to this very narrow triangular cross-sectional shape. Okay, so with this, we conclude today's presentation, today's webinar. I hope you liked it. I hope you would like to try it and test it on your examples. And now, before we go to Q&A, I will give a final word back to Michael. Thank you all.